we continue with mass. When we talk about mass, what does it mean? The mass of an object, the mass of an object is defined as a measure of its inertia, as a measure of its inertia. So the question is this: what does inertia mean? Inertia is defined as reluctance to motion. Is defined as reluctance to motion. What this basically means is that the mass of an object, which is a measure of the object's inertia, the more massive an object is, the more that object will resist motion. That's why it is said that inertia is a measure of the inertia of, that's why it is said that mass is a measure of the inertia of an object, which is the reluctance to motion. So more massive objects will definitely have more inertia. Now, that now takes us to momentum. If a particle is moving, the mass of that particle is moving at a particular velocity. Therefore, that particle gains momentum. So, if a particle is moving, the mass of that particle is moving at a particular velocity. Therefore, the object is said to be gaining momentum. Therefore, we define momentum. Momentum is defined. So, momentum is defined as the product of mass and velocity. So mathematically, the symbol for momentum is P, and is defined as the product of mass and velocity. So let me put down the momentum P. Momentum is defined as the product of mass and velocity of an object. So momentum mathematically is defined as product of mass and velocity. So question: if an object is moving at a particular velocity and the object gains momentum, or the object loses momentum, that means that the momentum of the object has changed. Which of these variables changes? Is it the mass of the object or the velocity of the object? Of course, the particle remains the same. So you don't expect the mass of the object to change. So if there is a change in momentum, it will be a measure of the change in velocity. So change in momentum, theta P, is the product of mass and the change in velocity. Is that okay? So question: a particle of mass 5 kg moving in the positive x direction at a velocity of 5 meters per second. The velocity of the particle is increased to 8 meters per second in the same direction. Calculate the change in momentum. Calculate the change in momentum of the particle. So the change in momentum here will be given as the product of the mass and the change in velocity. So the change in momentum, the mass there is 5 kg. The change in velocity will be 8 minus 5. So you have 5 times 3. The change in momentum becomes 15 kilogram meters per second. Question 2. A particle, all right, a ball of mass 30 grams moving in the positive x direction at a velocity of 5 meters per second strikes a rigid wall and rebounds in the opposite direction at a velocity of 3 meters per second as shown below. Calculate the change in momentum of the ball. The change in momentum of the ball. So we have a case of a ball of mass 30 grams moving in the positive x direction with a velocity of 5 meters per second. It struck a wall and rebounded with a velocity of 3 meters per second. So we want to find the change in momentum. The change in momentum becomes the product of the mass and the change in velocity. What is the mass? 30 grams. We take it to kilograms. This becomes 0.030 kilograms. What is the change in velocity? The change in velocity becomes v2 minus v1. That becomes, this velocity is in the negative x direction. So that becomes minus 3 minus 5. So you have 0.030 times minus 8. This becomes minus 0.24 kilogram meters per second. So we can say that the change in momentum of the ball is 0.24 kilogram meter per second in the negative x direction. So that becomes 0.24. So i.e. I can write it as 0.24 kilogram meters per second in the negative x direction. So if you look at this question now, here, since the particle was moving in the same direction, the velocity of this one is still plus 8. The velocity changed from plus 5 to plus 8. So the change in velocity is plus 3. But here the velocity changed from plus 5 to minus 3. So the change in velocity is minus 3 minus 5. Very important whenever you are discussing momentum. Momentum is the product of mass and velocity and not the product of mass and speed. So velocity is a vector quantity. It has both magnitude and direction. Okay? Alright. So very quickly, so that is it there. 0.24 kilogram meters per second in the negative x direction. So very quickly, we move to the principle of conservation of linear momentum. We move to the principle of conservation of linear momentum, which is principle of conservation of linear momentum. So what this principle basically states that this principle is applicable in a system of colliding bodies. In a system of colliding bodies. So if you have a system of colliding bodies and there are no external forces acting on the system, what are examples of external forces? Like friction, gravity, air resistance. The only force we are considering is the force the particles exert on themselves when they collide. That's the only force we are considering. The force the particles exert on themselves when they collide. So if you have a system of colliding bodies, their total momentum before the collision will be equal to their total momentum after the collision, provided there are no external force acting on the system. That is the principle of conservation of linear momentum. In a system of colliding bodies, the total momentum before the collision is equal to the total momentum after the collision, provided there are no external forces acting on the system. When we say there are no external forces acting on the system, it means that the system is closed or isolated. So we can write, it states that in a system of colliding bodies, the total momentum before the collision, the total momentum before the collision is equal to the total momentum after the collision. Provided no external force acts on the system. So that is the principle of conservation of linear momentum. In a system of colliding bodies, the total momentum before the collision is equal to the total momentum after the collision, provided no external force acts on the system. i.e., in a closed system, the total momentum is constant. The total momentum is constant. For example, question 1. A particle of mass 5 kg moving in the positive x direction at a velocity of 4 meters per second collided with a ball of mass 6 kg moving at a velocity of 2 meters per second in the opposite direction. After collision, the 5 kg mass moved at a velocity of moved at the velocity of 0.5 meters per second in the positive x direction. In the positive, or let us, at a velocity of 1.5 meters per second in the positive x direction. Calculate the velocity of the 6 kg mass after collision. So what is basically explained is that we have a 5 kg mass moving at a velocity of 4 meters per second it collided with a 6 kg mass moving at the velocity of 2 meters per second in the opposite direction. After the collision, the 5 kg mass moved at the velocity of 1.5 meters per second. We don't know the velocity of the 6 kg mass after the collision. So we call it, we are looking for V there. So the total momentum of the particles before the collision is the sum of their separate momentum. So this becomes momentum is product of mass and velocity. So you have 5 times 4 here, plus the momentum of this is 6 times minus 2. Because the product of the mass and the velocity is in the negative x direction, is equal to the momentum after the collision, which is 5 times 1.5 plus 6 times v. So this becomes 20 minus 12. 20 minus 12 is 8. 8 is equal to 7.5. Is equal to 7.5 plus 6v. Okay? So if we collect like times, this is going to give you 0.5 is equal to 6v. Therefore, v becomes 0.5 over 6. 0.5 over 6 meters per second. So this becomes 0.8, 0.083 approximately meters per second. So that is what that will give you as the final answer. We'll take the next question, which is question 2. Question 2. Question 2. A ball of mass m collided moving in the positive x direction at a velocity of 10 meters per second, collided with a ball of mass 2m moving in the opposite direction, with a velocity of 0.5 meters per second. No, with a velocity of 3 meters per second. After collision, the two balls stick together. The two balls stick together. Calculate the speed at which they moved after collision. Calculate the speed at which they moved after collision. So this is a case in which the two particles coalesced after collision. To coalesce them means that the two particles stick together after collision. So I can say the body of mass m moving at the velocity of 10 meters per second in the positive x direction. It collided with the body of mass 2m moving in the opposite direction in the velocity. With the velocity of mass moving in the, let's use same direction there, so that you don't, some people don't think that they're always moving in the opposite direction. Moving in the same direction with the velocity 3 meters per second. So I have to change the direction of the arrow here. Moving in the same direction with the velocity of 3 meters per second. After the collision, the two balls stick together, m and 2m, and they both move with velocity v. So we are looking for v. So the total momentum before the collision will be the sum of their product of mass and velocity. So this becomes 10m times 10 plus 2m times 3. The velocity, they are both in the same direction. They are both in the positive x direction. So this plus is also plus. Is equal to what? M plus 2m. The two bodies stick together after the collision. So it became a coalesced body, or a composite body, having a combined mass of m plus 2m and moving with velocity v. So this gives you 10m plus 6m is equal to 3mv. So I have 16m is equal to 3mv. This m takes this m, v becomes what? 16 over 3. What is 16 over 3? 5.3 meters per second. Okay? So the things that we have been considering so far, what we have been considering so far is the conservation of linear momentum in the same direction. What we have been considering so far is the conservation of linear momentum in one dimension. What we have been considering so far is the conservation of linear momentum in one dimension. Is it possible that the particles, their momentum is in two dimensions, either before or after the collision? It's very possible. And that is the next thing we now want to explain, which is conservation of momentum in two dimensions. So we now look at this, which is conservation of linear momentum in two dimensions. So I'll just use a question to take care of that, to explain it. Because when we are looking at the conservation of linear momentum, it simply means that in a specific direction, the momentum is conserved. So let us say we have a body, a 5 kg mass, moving in the positive x direction with a velocity of u substitute a. It collided with let's say this is 10 kg, collided with a body of mass 5 kg, moving in negative x direction with the velocity of u substitute b. After the collision, the 10 kg mass moved at a velocity of VA at an angle of 30 degrees above the x direction, and the 5 kg mass moved at a velocity of v substitute b at an angle of 60 degrees below the x direction. So the question we now want to find out now is for you to find V and VB. So let me give values to UA and UB. So let's say this is 4 meters per second in this direction, and this is 5 meters per second in this direction. So let me give value to them. So the question now is to find VA and VB after the collision. If you look at this, before the collision, the momentum of the particle is only in the x direction. Before the collision, the momentum of the particles is along the x direction only. After the collision, the momentum is now in two dimensions. along the x here, after the collision, it will be VA cos 30. Why this one will be VA sin 30? That is their velocity component along the x and along the y after the collision. Why for B, after the collision, the momentum is in the negative because this angle is 60 degrees below the x direction. So this will be VB sin 60 degrees. Why this will be what? VB cos 60 degrees. So we have to pick the specific direction we are looking at the conservation linear momentum. So conservation linear momentum along the x. Conservation of linear momentum along the x. So that will give us 10 times the product of mass and velocity along the x before the collision, which will be 10 times 4 plus 5 times minus 5 along the x before the collision will be equal to the total momentum along the x after the collision, which will be 10 VA cos 30, that is positive x after the collision, plus 5 VB cos 60 degrees after the collision. The component of the velocities along the x after the collision, both of them, they are along the positive x direction. So this will give me 40 minus 25 is equal to 10 VA cos 30 is root 3 over 2 plus 5 VB 1 over 2. So this will give me 5 VA root 3 plus 2.5 VB. 40 minus 25, that is equal to what? 15. This is equation 1. So I cannot solve the equation I cannot solve for the two unknowns using a single equation because already I have two unknowns. Therefore, I have to look at the conservation of momentum along the y. Conservation of momentum along the y. Okay, so if you look at that, the total momentum along the y before the collision will be 10 times 0. Why is it 10 times 0? This velocity is in one direction before the collision. It has no component along the y. Plus 5 times 0. This velocity is also along the x. It's in one dimension. It has no component along the y. Is equal to 10. This velocity after the collision, this velocity after the collision has a component along the y after the collision, which is VA sin 30 plus 5. This velocity has a component along the y after the collision, which is minus VB sin 60. So this becomes 0 is equal to sin 30 is 1 over 2. So that becomes 5 VA minus 5 VB sin 60 is root 3 over 2. So this basically will give you 0 is equal to 5 VA minus 2.5 VB root 3. I call this one equation 2. So from this equation 2 now, I can easily say that 5 VA is equal to 2.5 VB root 3. So VA becomes 2.5 divided by 5. That's 0.5 VB times root 3. I can call this one equation 3.